Hello everyone. We've been talking about electron configuration and how those are put together and how they're arranged around the nucleus. This can also lead to a different discussion on something called periodicity. And the periodic table qualities, or the arrangement of the periodic table, is based on this concept of periodicity. And it says that the properties of the elements and their patterns on the periodic table are a function of their atomic number. So again, their atomic number yields our electron configuration. So even the electron configuration gives us different patterns. But again, the idea is that the atomic number is really what dictates where these things are on the periodic table. Now, periodicity involves a periodicness, a periodic quality. In other words, a repetitive pattern. These are not the predictable patterns that we are used to seeing. For example, 7 days in a week, 12 months in the year, essentially four seasons in a year, that kind of thing. They're a little bit different. What we are going to use are going to be the blocks of the periodic table. Okay. So the first trend I want to talk about is something called the effective nuclear charge. We affectionately call it Zeff. Okay, Z is the atomic number Z. So this is the effective nuclear charge, and since the atomic number is the number of protons, and that's the nuclear charge, the charge in the nucleus is because of the protons, we call it Z, or the effective nuclear charge, Zeff. So Coulomb's law states that the pull of the nucleus on the electrons is dependent upon two things: the net nuclear charge, in other words, how positive the nucleus is, or how many protons you have, and of course the distance from the nucleus. Okay, so the closer, so if I have a nucleus here and I have electrons really close, and I only have a couple protons, or maybe I have many protons, these electrons are held really tight to the nucleus because they're so close. Take the same nucleus and now put electrons out here in these further orbitals, and now they're held much more loosely. Okay, so again, how many positives do I have in here? That's the first point. The net nuclear charge. The net nuclear charge is always positive, and then the distance those electrons are from that nucleus. So there's a plethora of attractions and repulsions on each electron in the electron cloud. In other words, they're pushing, they're pulling, they're attracted, they're repelling. Oh my gosh, there's so many going on. So anytime I have a many electron or a non-hydrogen atom, there are these unpredictable attractions and repulsions and forces going on these electrons. So we can see that the atom actually flexes. An atom is not necessarily a rigid marble or steel ball bearing. It's actually a flexible electron cloud that almost pulses, okay, in and out. So we have to consider the average there. The big, the small, we're going to consider the average size, okay? We just talked about the shielding effect, which is where the core inner shell electrons block or shield the outer electrons. Again, that has to do with more core electrons, the greater the shielding effect, okay? This also dictates size, or leads to size a little bit here. So what are Zeff trends? So the effective nuclear charge is dependent upon those two things, not only how many positives are in the nucleus, but also how far those electrons are away from that nucleus. So we would see that the effective nuclear charge increases across a period because there is increasing nuclear charge with no accompanying shielding effect. So if we take a look at a periodic table, if I'm on the fourth period and I move down that fourth period, the pluses keep adding up one after the other, right? Every time I go from one element to the next, I keep getting a positive proton. But I'm staying in the fourth energy level, so the shielding effect gets no greater. Okay? Remember, shielding effect is dependent upon the orbitals, or the shells that are the energy levels, excuse me, that are in front of it. Well, since I'm staying in the fourth energy level, I'm not adding any energy levels. So the shielding effect effectively is moot at this point, and we see that the Zeff also increases and pulls the electrons tighter and tighter and tighter. What does that do to the size of the atom? It means the atoms get smaller and smaller and smaller as we move down a row. Okay, more on that in a little bit. They decrease down a group because the nuclear charge increases down a group. The shielding effect is way more of a factor. Okay, so Zeff increases to the right and down a group. Okay, now the size of the atoms, or this is the bonding atomic radius. In other words, we're going to consider things that are bonded, not just alone. Again, and we're also going to consider the average. We'll also only consider the main group elements, the S and the P blocks. So let's take a picture. Let's take a look at that here in a second. So notice our trends here. Just the P blocks. Here's the S block on the left and the P block on the right. You can see those there. Notice how as I move to the right, as I just talked about in Zeff, since Zeff increases to the right, the effective nuclear charge increases down a period without, or as I move to the right on a period, since Zeff is increasing, or the effective nuclear charge, in fact, is increasing, Zeff is increasing, okay? In other words, the effective nuclear charge, okay? Which makes the atoms smaller as I progress to the right on a periodic table. I'm not giving them any extra room to roam here in whatever energy level I am in. I'm not giving them any extra room to roam. And the shielding effect is, again, a moot point because I'm still in the same orbit. I'm still in the same energy level, okay, if I'm just considering staying in the 4th energy level. So they get smaller as you move to the right. And as I move down a group, notice they get bigger. I'm adding energy levels, so that should make sense. Okay? So the group trends, atoms get larger as we move down a group, more energy levels. And the period trends say that atoms get larger as we move to the right on a period or a row. Why? As F increases, it draws the valence electrons in closer to the nucleus, and the atomic radius decreases. So don't forget, every time I add a positive to the nucleus, and I'm not increasing the shielding effect, the atom should shrink, okay, as I move to the right block by block, or element by element, okay? Okay, ionic radii, and we're done with this video. Cations are smaller than their metal atoms that they come from because they've lost electrons, so they'll shrink. Lose electrons, lose weight, get smaller. Anions are bigger than the nonmetals they come from because they have gained electrons. Gain electrons, gain weight, get bigger. Now again, this has to do with Zeff again. So if Zeff says that if I have, for example, the sodium atom, which has 11 protons, oopsie, I put it in the wrong spot. The sodium atom has 11 protons and 11 electrons. There is a certain amount of balance here between 11 and 11. If I lose, again, you don't lose protons. If I lose an electron, now the Zeff is greater. The effective nuclear charge has stayed the same. So now that effect is now greater because I only have 10 electrons to distribute around there. Okay? So, and this is the opposite. Zeff increases when I create a cation. But anions are opposite. Zeff goes down because now I start off with a metal atom. For example, if I have 17 protons and 17 electrons in chlorine, now I have 17 protons because you can't gain or lose protons very easily. But now I have 18 electrons because I've gained one. Now I have this being distributed over this. So the effect of those positive 17 positives is much lower. Okay? Now, just remember, if we're going to follow this, all group trends are identical to atomic radii, and we'll talk about these more problem-solving things at the bottom of the slide in class, okay? Let me know if you have any questions.